Greetings. Let's take a look here at length contraction as it relates to special relativity. So the big thing with length contraction, we're not going to spend a lot of time doing the math because it relates back very similarly to the to the time dilation. But if you're curious, you want to see the derivation, you can look it up online or you can ask, and I'll be happy to run through that with you. But as a reminder, we have this relativistic factor gamma, and that's going to be equal to 1 over the square root of 1 minus v squared over c squared. So if that's our gamma, for length contraction, basically what we have happening is if an object is moving or something is in a different frame of reference than you are, and you see it traveling past you, it's going to be squished or contracted in the direction of its motion. So the classic example is a train. So if I've got a train traveling along, and say when it's at rest or when you're in the same frame of reference as it, you get some length, some proper length here. So if there's some person watching it, they see some proper length. If that same train is moving now with some speed v, then that person is going to instead measure it with some new observed length. So what happens is the train does in fact, for all intents and purposes, from the perspective of the person standing there, if you are in that frame of reference, the train does get shorter. It does get contracted along this direction of motion. It won't get shorter vertically, just in the direction of this velocity. And the relationship between those two lengths is that the observed length will be equal to the square root of 1 minus v squared over c squared times the observed length, or if we use that gamma factor, the observed length is equal to the proper length divided by gamma. And if you remember, gamma is always going to be greater than 1 because v is always going to be less than c, which means 1 minus v squared over c squared is always going to be some number less than 1. Square rooting it means it still stays less than 1, and 1 divided by a number less than 1 has to be greater than 1. So we're always going to get this length getting shorter or getting contracted. So just as a reminder, we've got proper length. We've got the relativistic factor. And we've got observed length. The proper length, again, is the measurement taken in the same frame of reference as where the object is. So in the case of the train, it's when the train is at rest or when you are at rest relative to the train, if you measure its length. The observed length is from any other frame of reference, and the relativistic factor is excuse me, what you see up there. So, as an example, a train is traveling down the tracks at a speed of 0.75 c. It approaches a tunnel that has a length of 100 meters. What's the longest the train can be so that it fits in the tunnel according to an observer standing on the side of the tracks? And hint, the observed length should be 100. What is the proper length? So we have this train, and we want to get a length of 100. So that will fit inside the tunnel that it's coming up to. And it's going to have some speed v equal to 0.75 c. So let's write out what our gamma is first. It's going to be 1 divided by the square root of 1 minus 0.75 c squared divided by c squared. The c's will cancel, and we get 1 minus square root of 0.75. So that will give us gamma is equal to 1 over the square root of 0.4375. And we take the square root of that, excuse me. We'll get a gamma of 0.661. So if we know that gamma is 0.661, we can set our observed length is equal to proper length over gamma. Sorry, it should be 1 over 0.661. And again, I was able to double check that for myself because we know that gamma has to be greater than 1. So when I saw the 0.661, that clued me into I had forgotten to divide. So this means that the proper length will be equal to the observed length times gamma. So the proper length will equal 100 meters times 1.512. So the proper length can be up to 151.2 meters. So if this train is traveling along at 0.75 and it's 151.2 meters long, the observer will see it go into the tunnel and we'll see it completely disappear within the tunnel here. All right, let's go over kind of a related paradox, and it shouldn't be a ladder, this should be a train, since I had changed that. So imagine the train in the previous problem. We found the train would fit in the tunnel, even if it has the longer proper length. Remember, it had a proper length of 151 meters, than the tunnel because of length contraction. So length contraction makes the train get shorter in the direction of its travel, so it fits within the train. However, if we imagine it from the frame of reference of the train, now the tunnel is moving. So from the train's perspective, it's 151 meters, and it's got this 100 meter tunnel traveling towards it with a speed of v. So now the tunnel contracts from what was originally 100 meters. Train wouldn't fit. Now the tunnel contracts even more, and now we're like definitely way short by a factor of about 1.5. So it's like, I think the tunnel should end up being about 66 meters long from the perspective of the train. You can run those numbers yourself. And so that means it's much shorter and the train can't possibly fit. So the question that I want to leave you with that we'll discuss in our time together is, which is correct? Does the train fit or does it not? Which perspective is the correct one? So we'll leave off there. If you have any questions, let me know, but otherwise have a great rest of your day here.